When we were discussing previously the typical valve topology or tube topology for a condenser mic, we're looking at bias supply, plus 60 volts or whatever, going down to this is the microphone capsule, then capacitor coupling off that into something a bit like that. Okay, we've got two high value resistors, two very high value and relatively expensive resistors, and a coupling cap that it's not allowed to be leaky.
Sure. So what type are we talking about?
Usually polypropylene, polystyrene, poly put the kettle on.
And what values did you need in there?
A nanofarad or so.
Oh, okay. Yep. That's doable in those technologies.
Basically, when you've got 50 puff and a nanofarad, then that doesn't represent much series loss.
Sure.
Yeah. When we went to the FET-based circuits, I wanted to try and get rid of one or the other of those resistors. I had a cunning plan.
Ooh, do tell.
Oh yeah. Which was this. First of all, get your JFET. You'll probably want to fix its bias with, you guessed it, a high value resistor.
Yep, higher the better.
Yeah, somewhere. Why don't we simply connect that to our microphone and a high voltage supply?
Yes.
Let's face it, the same.
It's exactly the same.
Yeah. So let's say that's sitting at, I don't know, 60 volts. Well, actually, no, I think we took that up to 90 volts, just for the hell of it. And let's say that's sitting here at 10 volts, and there's a good reason for that sitting at 10 volts. We get 80 volts across there.
Yep.
We get one resistor only. As long as we don't have any leakage in the microphone capsule, the gate is sitting at 10 volts, and we've gotten rid of an expensive resistor, a surplus capacitor, and in principle, what we should have with a typical depletion mode JFET, if that's at 10 volts, that might be at, say, 10.2 volts or 10.5 volts or whatever. Let's use that as the front part of a closed loop unity gain voltage follower.
Okay, let's do.
So what we might do here is put a resistor there. We'll put a PMP transistor there as a voltage gain stage. I'll come back to that in a second. We'll load that with a current source.
Yep.
Okay.
What typically would you have made the current source out of? A couple of trannies?
A resistor.
Oh, resistor. Fancy. All right.
Well, actually, you can go anywhere from a resistor to a proper current source.
Right.
And in various models, I used various different topologies. Now, in actual fact, I was using about 15 volts there, about 7 volts there. That was sitting at about 7.5 volts. That was slightly higher than that.
Yep.
Then what we did there was, this is going to look disturbingly like a power amplifier. Let's put basically a bias voltage in the middle there and take it off to a
It is. Yeah, it is.
It's a power amplifier. Okay, we've got a voltage amplification stage there. We've got a bias. Incidentally, red LEDs are good for that.
Yes, they are.
Yep.
Although LEDs can be noisy.
I never came across a noisy one.
Okay, right.
Certainly the red LEDs about 1.5, 1.7 volts. Which allowed, 0.6, 0.6, and a few 15ths of a voltage across there. Yep. So that's our output. And what do we do with that? Bang, straight on there.
Yep. That's to minimise the crossover distortion, of course.
The bias is to
Yeah,
minimise the crossover
crossover
distortion.
Yep.
Now, let's just say we've got, say, a 1 milliamp current source down there, or maybe even a 6K8 resistor. The value of resistance there will determine the FET current. Basically, let's just say that we have a 1K resistor there. That transistor is going to require about 0.6 volts to turn it on. So guess what?
Yeah.
We're going to get about 0.6
You will.
milliamps down there. If that tries to pull more than 6 milliamps, it's going to increase the voltage there. That'll pull that lot up. It'll bring that point up. It'll shut that device off, relatively speaking. So that's the resistor which sets the operating current for the FET. Its operating voltage is set by the fact that that voltage there is 0.6 of a volt less than the supply, and that voltage there is going to be slightly more than the bias voltage. And it's the bias voltage here which sets the output voltage. All the quiescent conditions explained, and boom, it's unity gain.
Nice.
And because it's unity gain closed loop, its linearity is exceptional.
And that's what you want in a good mic. Yep.
Now, the other thing is, I was discussing previously the role of capacitances, and I said that we were typically about 10 puff there, about 30 puff there.
Yep.
That 10 puff there, is it bootstrapped? Not on your Nelly, because it doesn't matter how big a signal we put there, the signal voltage there is naff all, so our capsule is loaded just by that 10 puff.
Right.
How about this 30 puff cap down here? It's a follower. There is no voltage across that cap. It's completely bootstrapped out.
Yep.
So our 50 puff capsule is really only seeing a bit of stray wiring and 10 puff.
Clever.
So relatively lower attenuation.
Very nice.
Now, let's talk about that NT3 microphone. It was just a little bit different because the...
So what was this? Was this used in?
Yes, that topology is used in, for example, the Rode NT1000.
Okay.
Or almost as shown.
Right. Okay. Right.
Yeah, bugger all difference. The FET, the JFET that we're using in the NT3, rumour has it was originally designed back in the mid to late 90s for use by the CIA in some of their little bug microphones, and was manufactured by Siliconics.
Okay.
I wish I could remember the part number because it's a cute little beastie consisting of the JFET and a pair of back-to-back diodes.
Okay.
Now, what do you do with them? Well, the first time I tried using that FET, I simply used it in the normal configuration where you ground that and you ground that and you pull current out the top. Those are horribly non-linear devices.
As you'd expect.
Yeah, more than about 10 or 20 millivolts of signal there, and it was basically non-linear as. Okay, why would you use those in the first place? Because they actually act very nicely as a replacement for a really high value resistor.
Of course, yes.
As long as you can keep the voltage across those low, they act like a high value resistor.
Got it.
How the hell do I use those? Well, the first thing I did, let's just whack a bit of resistance in there, and maybe a meg or something like that, and connect that to
so these came out as a separate pin.
Yes, it was a 4-pin device.
Right, okay.
There, and of course, there.
Nice.
One of the selling features of them was really low input capacitance, incidentally.
Got it.
And I figured I'd use these because, again, it gets rid of what was at that time a relatively expensive, very high value resistor.
Yep.
But how to use it? Bootstrap the buggers. 1 meg resistor to our bias supply, and then connect that to a capacitor, which goes, you guessed it, to basically the source connection.
Yes.
So that
it vanishes.
Yeah. So that was one of the really cool things. Maybe somebody on the
All
blog...
to save cost?
Not only to save cost, but it was a convenient little package.
Right,
and
okay.
if we pull this out, you'll be able to see it living up the front just there.
Yep, that little 5-pin SOT 23.
Yeah.
Right.
And look, maybe somebody can do a bit of research and tell us all what the hell the part number on that is, because I can't find it anymore. It doesn't appear on data sheets anywhere.
Bummer.
But that was an interesting little circuit tweak that saved us a resistor. The other one was...
and these aren't 0.00001 cent resistors.
Yeah, they're like, even in volume, we might be looking at 30 cents or thereabouts cost, instead of 0.005 cent.
Yep.
So saving, pulling 30 cents out of the product cost is, it's an exercise worthwhile doing.
Absolutely.
Particularly if you can do it at the expense of, a 0.005 cent resistor and maybe a 1 cent capacitor.
Yep.
Yeah. Oh, let's close the loop.
Yes.
Okay. The initial prototypes of this microphone, well, they went out for beta testing. Comments came back, they were a bit lackluster up in the top end.
Right.
They didn't have enough kind of pizzazz, not enough excitement. And basically,
not enough distortion.
the frequency response...
It was too flat. It was
The frequency response looked a little bit like that, where those ripples were up in the kind of the 15 kilohertz plus region.
Your ripples aren't big enough.
Exactly.
You've got to have big ripples.
Yeah, well, big ripples. And basically what they wanted was a bit of extra excitement up here, a little bit more psst, at about 6 kilohertz
Is that
or above.
what you added to the data sheet? Extra excitement?
Yes. Well, no, we had
The new model adds excitement.
we had to add some more psst, some more quack quack. So we've got the perfect opportunity here to do a little bit of finessing, because it is a closed loop circuit. So I kind of scratched my head and walked around in circles for a while and opted to put in a bridged T circuit
right, yes.
in the feedback network. Now, bridged T network has a response that looks like that. It's got a rather minor notch, which when you use it in a feedback network gives you guessed it.
Yep. Ooh, little peak.
So these microphones have
Yeah.
that little bridge T circuit in them, just to add a little bit of woohoo to the sound.
How did you choose the frequency you were going to put that at?
Basically, the knowledge that they wanted a little bit more woohoo. And, the sales guys who were there at the time were kind of canny enough to realise where it needed that little bit more pizzazz.
Right.
And we did a couple of different cut and tries to find out, first of all, how much, and secondly, at what frequency. And yeah, it was around about the 6 kilohertz mark that they wanted the extra squirt.
Okay.
And I think about 4 dB, thereabouts.
So, am I just a bloody amateur? Because if I'm looking at the microphone data sheet, I want to see this flat. I'm going to buy the one that's flat as a tack.
Bap!
I'm an amateur. Clearly, I don't know what I'm doing.
No. If you're after a microphone as a measuring instrument,
Yeah, of course.
you want dead flat.
Absolutely.
If you're after a microphone to measure, to record something like an orchestra or something whose sound was absolutely defined and known, and you didn't want to muck about with it, pick something flat.
Yep.
That's not what happens in studios. Studios are creative environments. You're trying to create the sound that winds up on tape, which is why you have this cupboard or room full of different microphones with different wobbles and different microstructures and different directional characteristics and different amounts of distortion, because you want to choose a creative tool that actually kind of sounds like what you really want it to sound like.
Are people still doing that in mics these days?
Oh, hell yeah.
Yeah? They're not doing it in the other end?
No, because look, everybody knows it's cheating to do it at your digital audio workstation.
Exactly.
Yeah, if you can't do it with a room full of $10,000 vintage microphones, what's the point?
Exactly, gold plated.
So anyway, that might be an interesting little trick for anybody who's playing with these. Oh, there's one vital component
What are we missing?
that I missed out of this circuit. It's a closed loop system, is it not?
It is.
It needs dominant pole compensation.
Ooh. There you go.
And without that, trust me, it oscillates like a banshee.
Yep. How did you pick
It
it?
screams.
How did you pick that?
Actually,
Did
basically,
you just stick it in until it works, or did you?
there is actually a perfectly viable technique that
Yep.
I use, which is from that
Does
onto
this work for any closed loop system that you would design?
pretty much, yeah.
Yeah. Okay.
Connect it to a SIG Jenny
Yep.
square wave. Okay, have a look at the output and find out whether it's going
Yep.
or
Like that. Yep. That's it.
yeah. Oh, bear in mind when
And you want it to optimise.
yeah, ideally
Yeah,
you're
you want
after
it
something a bit like that.
Just tape it, yeah. Just
Yeah.
rounds off
Yeah.
the corners. a little
You want to get it up to the point of maybe a small amount of overshoot,
Yep.
in which case you know that it's pretty good, it's pretty stable.
Right.
That is not on
No.
because
Yep.
production variations it's likely to turn into
And oscillator.
that.
Yep.
Yes.
Yep.
Trap for young players though, there's two kinds of stability issue that you need to worry about in any of these power amp circuits. One is the loop stability,
Yep.
as governed by your dominant pole compensation, or you can go for split pole compensation.
Yeah, there's many different. Yeah.
But the other one involves the simple fact that emitter followers, voltage followers, are renowned for oscillating by themselves
Yes.
as a form of negative impedance oscillator whenever you hit them with a capacitive load.
A big capacitive load. Yep.
And when you get that happening in, for example, an audio power amplifier, a big one, you can first of all start isolating
Yeah.
the
You can.
inputs with ferrite beads to raise the source impedance at high frequencies. You can add emitter degeneration.
You can
and
do that
you
with
can-
ferrite beads. They're up in the hundreds of megahertz.
Oh yeah, look, I've had 4 megahertz bandwidth transistors sitting there. One
Yep.
4 megahertz bandwidth output transistor sitting there, just mounted on its own on a chunk of heatsink,
Yeah.
and just with I think it was 2 resistors and a capacitive load, I turned that into about a 30 or 35 meg oscillator. And I could tune it by getting my source wire and just running it up and down the length of heatsink.
Nice.
Yeah, so yeah, nasty. And that's just all about parasitic inductances and
Yeah.
stuff like that. Any parasitic inductance up in here is to be avoided, whereas any parasitic inductance here is to be appreciated.
Yes.
Sometimes even some local degeneration
Yeah, you can.
there. It depends. But there are these two forms of stability. One involves the loop, the other involves just the output stage acting as a follower with stray inductance here and low impedance at the bases, and it forms I think a Colpitts or a Hartley oscillator or something like that once you hit it with some extra capacitance over there. Yeah.
Yep.
Okay, so that's the basics of a lot of the microphones currently being manufactured by Rode.
Rode.
Yeah.
Terrific.
Now, let's go one step further. Okay, we got enough time?
Yep.
This is really cool. Okay, so we've
15
pretty
minutes.
much got the same circuit that we had before,
Yep.
with the bias network of your choice in the output stage and yada yada yada. What we're actually going to do here is something dirty, 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 dirty.
Like the sound of it.
Let's ground that. Let's take this down here to minus 120 volts.
Yep.
Okay.
You haven't changed anything so far.
No, we've put in some. I'll get rid of those
get rid of
because
that.
we don't need them. We do, however, need that one.
Yep.
Do you know of any high voltage FETs that'll go in there that'll run at like 120 volts?
Ooh.
I do.
Not offhand.
I do. They've got pilot lights
Oh,
inside them.
there we go.
Oh, yes.
You're a tube fan.
Well, this was for the NT1000.
Right.
And yeah, sorry people, it's another Heretics microphone. It's got a tube front end, but it's riddled with bipolar.
And there's a very sensible reason why you did this.
Oh yeah. First of all, okay, that goes off to the output through capacitive coupling, yada yada yada. Okay, I want something that gives, this is a non-inverting of course, and I wanted this particular circuit to react such that, how do you put it, positive pressure into the microphone gave a positive output.
Right.
Best way of doing that was
there any absolute need for that?
a distinct preference.
Right.
Okay, let's put the microphone there
Yep.
and bias that through our 5 gig resistor to a voltage of about minus 60. Okay, guess what? Any positive pressure input there, okay, moves the plates closer together, voltage goes up, polarity, beautiful. Okay, why these inverted voltages? Why ground up there and minus 60, minus 120? First of all, it keeps the metal parts of the microphone substantially at 0 volts.
Okay.
Just quietly, there is one other microphone that we did where that's actually sitting at plus 60, and if you operate it with the cover off and put your lips on it, you will get a belt.
Right.
Mind you, who'd be stupid enough to run it with the cover off? I don't know.
Right.
But this circuit was absolutely fearsome in its dynamic range.
Right.
First of all, with those supplies, we could get an output voltage there of about 35 volts RMS.
Nice.
Not bad for a microphone preamplifier.
Pretty good.
35 volts RMS is
That's RMS, that's not peak.
probably about 2 orders of magnitude higher than most line inputs will cope with. That had implications for, how do you put it, the maximum SPL that you could apply to the microphone capsule. In fact, you can put, I think it was about 150 something dB SPL on the mic capsule.
So you're physically limited by the mic capsule, not the circuit.
Yeah. Secondly, if you pick the right operating current, again the operating current's determined by that resistor there, pick the right operating current for that valve, and the residual noise of the system corresponded to a, how do you put it, a microphone, a noise at the microphone of about 12 dB. You can express the system noise in terms of how much acoustic noise does that correspond to. So we had 12 dB SPL equivalent noise. We had, I think it was about 100, let's call it 155 dB SPL at, and this wasn't a clipping, this was at like 1% distortion.
Wow.
Okay, subtract that from that and you get a dynamic range of, what's that, 143 dB dynamic range out of the one circuit. Now there's not too many semiconductor circuits that'll do that, and here's a tube circuit with that kind of dynamic range.
Awesome.
Hey! And one of the tests I did, now you have to do this.
You have to test it.
I simply hung a set of headphones off the output there, and it worked bizarrely well. It was loud in headphones.
Right.
Incidentally, because I wanted this thing to be capable of feeding 600 ohm loads, it's actually got 2 sets of paralleled output devices so that it can actually drive a 600 ohm load at those kinds of levels. So
from the mic. From the mic. That's disgusting. Did anyone actually use it? Did anyone actually use it for this, or was it just design overkill?
It's pure design overkill. It might be pure onanism on my part, but incidentally, that noise figure there, that was based on optimising the operating voltage and current so that it would suit a very wide cross section of tubes.
Right. Okay.
I could have dropped that noise probably about 4 or 5 dB if I'd tuned the operating current for the valves. But if you do that, you make the thing kind of unproducible. But yeah, getting that down to about, we could get that down to about 8 dB SPL.
Wow.
The best commercial semiconductor mics are probably the Rode NT1A, which is about 3.5 or 4 dB noise. The Neumann TLM103, I think it is, which sits around about 5.5 or 6 dB. That kind of order of magnitude.
Yep.
We could get this tube thing down to pretty close to the best that semiconductors had to offer.
With that ridiculous
that kind of output level.
That's ridiculous. How did you get these in production though? Who did you get them from? How can you still get them? Nobody's making tubes.
Yes, they are. Yeah,
they are. They're still making them?
Svetlana people like that.
Right.
There's a few companies making tubes, and there's two different types. You can get the new old stock.
Yeah.
It's probably been manufactured back in 1970 and just kept in a warehouse.
Russia, yeah.
And then there's the actual new tubes.
Right.
And I think what Rode are doing, they're using new tubes, but they age them quite viciously. They operate them at quite high voltages and currents to burn them in so that when they actually put them in a mic, they're going to be stable for a very long time.
Got it.
It's something that they do quite well.
How much power were you pissing away heating this thing up?
I was slightly underrunning the filament. They're normally a 6.3 volt filament. I think I was running them at about 5.5 volts or thereabouts, just slightly under. If you run too far under, you start stripping the thorium or whatever off the cathodes.
Right, yeah.
And can't remember, about 300, 500 milliamps. I think. They don't draw huge amounts of power.
Right.
Yeah,
but how are you getting this from the Phantom? Powers?
Not from Phantom.
No.
Not this valve one.
Not this particular
specific
valve mic.
Power supply.
Right, you're right.
And even the power supply had some quirks to it. The topology for the power supply, just very quickly, we'll finish up on this, I think. Okay, again, negative power supply.
Yep.
So ground up the top and a negative unregulated voltage down here. The first thing we created was a current source, well actually a current sink. Okay, so over here we've got our main reservoir caps off the bridge rectifier.
Right.
A current sink consisting of basically an N-channel FET.
Yep.
And connected across it a amplified Zener, again consisting of an N-channel FET. So what do we have out here? First of all, that's low impedance, that's high impedance. Any ripple there is severely attenuated there.
Got it.
We had maybe hundreds of millivolts ripple there. We were lucky if we got tens of microvolts ripple over here. And of course you can picture that this topology probably looked a little bit like amplified Zener.
There you go.
And this one, of course, consisted of, I might as well draw him down here, one of them. I'm sure you've seen that one before. And a bias resistor up to who cares.
Yeah, too easy.
And that creates a current source, amplified Zener.
Yep.
Nice little supply, which is intrinsically short circuit protected,
Yep.
because that simply soaks up
It does.
any short circuit current. and has devastatingly low noise out there.
Fantastic.
So, yeah.
It's a win all round.
One of you out there somewhere might have call to use that kind of topology one day.
There you go.
I hope.
And all Rode mics are still designed and built this way.
Yeah.
Fantastic.
To the best of my knowledge. Mind you, it's what, 13, 14 years since I've been there, but to the best of my knowledge, any of their high-end studio stuff still uses these techniques.
Beautiful. Thanks, Dougie.